We just saw how to find the local extrema, so now let's work on absolute extrema. Our extreme value theorem tells us that if we're looking at a continuous function over a closed, bounded interval, we know that there will definitely be an absolute max and an absolute minimum, and that's because we get to use the endpoints of our interval. So our next theorem for location of absolute extrema says, let's talk about a function f that's continuous over a closed bounded interval I. Then the absolute maximum for this function either comes from the endpoints of the interval, so the left side of the interval or the right side of the interval, or the maximum minimum will come from the critical points. So this tells us that anytime we're going to look for absolute extrema, we need to not only check the critical points, we need to also check the endpoints of the interval that we're looking for the absolute extrema on. The book provides us with a problem-solving strategy for how to do this. The first step is to check the values of the function at the endpoints. So if the closed interval is from a to b, I need to plug a into my function, calculate it, plug b into my function, calculate that, because those endpoints could be the absolute max or the absolute min. So step 1, evaluate the function at the endpoints. Step 2, find all the critical points that are inside of the open interval from a to b. This is super important because sometimes when you're looking at absolute extrema, you're only looking at a small window. The interval I, for example, does not cover the entire function. So if you find all the critical points for the function everywhere, some of those critical points might not exist in the interval that you're talking about. So find your critical points and then check to see that they fit inside of the interval from a to b. Then, once you find those critical points, we're not going to bother graphing the function to determine if they are max or min. Instead, we're just going to evaluate our function at those points, because our third step is to compare all of the values found in step 1 and in step 2. So we're going to make pretty much a table of values, and we're going to compare the function value at the left endpoint, the function value at the right endpoint, as well as the function value at any of the critical points inside of that interval. The largest value out of all of those is considered our absolute max, and the smallest value would be considered our absolute minimum. Let's give this a shot. We've got two functions on the screen. We're asked to find the absolute maximum and absolute minimum over the given interval. So let's start with the function f. Step 1 is to find the value of the function at each of the endpoints. So we need to calculate f at 1 and f at 3. Let's go ahead and do that. When I plug 1 into the function, I'm getting 0. And when I plug 3 into the function, I get -2. So that is the left and right endpoints. Now we can move on to step 2, which is find all the critical points inside of the interval from 1 to 3. So our derivative will look like -2x plus 3. Set that derivative equal to 0. We find that x needs to be 3/2. And just to be sure, we need to double check, is this inside of the interval from 1 to 3? My question mark looked like a 3 there. There we go. 3/2 is like 1.5, and 1.5 definitely lives within the interval from 1 to 3. 1.5 would be like right here. So yes, our critical point is inside of that interval, so we should consider it. We need to now evaluate our function at that point, at 3/2. So we'll have negative 3/2 squared plus 3 times 3/2 minus 2. So we've got negative 9/4 plus 9/2 minus 2. Negative 9/4 plus 9/2, that's equal to positive 9/4 minus 2. I'll write 2 as a fraction, so that would be like 8/4. So we get a positive 1/4. Step 3 said to compare all of these critical values. So at x equals 1, we had 0. At x equals 3, our function was negative 2. And at x equals 3/2, our function was 1/4. From this list of values, we're going to identify our minimum and our maximum. So for locating absolute extrema, it's a 3-step process. Step 1, evaluate the function at the left and right endpoints. Hold on to those function values. Step 2, find the critical points. Check that they're inside of the interval that you're working with. Then evaluate your function at those critical points. Step 3, compare all of the function values that you calculated in step 1 and step 2. Pick the smallest one to be your minimum and the largest one to be your maximum. If you were paying attention very closely, you might have noticed that there's a small change in the g of x function, the exponent. I realized that I had typed it in incorrectly, so I went and fixed it. So let's work on this function g, same process that we just used for the function f. Start off by evaluating our function at 0. Plugging 0 into this function, we get 0 back out. Plug in the right endpoint, 2. That gives us 2 squared minus 3 times 2 to the 2/3, which looks like 4 minus 3 to the cube root of 4. And if we want to, we can plug that into our calculator, and we'll find that this is approximately equal to negative 0.762. Now, it is good to approximate this because we're going to compare these numbers to all of the other function values that we find in step 2. And looking at this expression here, we might have a hard time deciding if it's bigger or smaller than the other values. So it's good to have that approximate to help us decide where it lands. Step 2, we're going to find our critical points. So we take the derivative of g. Find that we have 2x minus 2 over the cube root of x. And if we get a common denominator, that becomes 2x to the 4/3 minus 2 all over the cube root of x. Now remember, we need to find where the derivative is equal to 0, and that comes from setting the numerator equal to 0. Move the 2 over to the other side, divide them off, we get x to the 4/3 is equal to 1. If we raise both sides to the power of 3/4, we see that x is equal to 1 to the power of 3/4, which leads us to see that x can be equal to positive or negative 1. And if we look at our interval, is this inside the interval 0 to 2? Well, one of them is, one of them isn't. So only x equals positive 1 is. We're going to ignore x equals negative 1 because we're not looking within an interval that includes that critical point. So we will evaluate our derivative at 1. Sorry, not our derivative, our function Evaluate our function at 1. We get 1 squared minus 3 times 1 to the 2/3. That's equal to 1 minus 3, or -2. We also need to recognize that our derivative can be undefined if we set the denominator equal to 0. This tells us that x equals 0 is also a critical point, so we need to evaluate our function at 0 as well, because 0 is part of the interval. It's a closed interval. But the good news is we already did this. Since it is the left side of the interval, we actually evaluated our function at that left endpoint in step 1. So our step 3 is to compare all of our values. We have g at 0 equals 0. G at 2 was equal to approximately negative 0.762. And then we had g at 1, which came out to be -2. So from each of these values to choose from, we can see that -2 is our absolute min, because it's smaller than the other two function values. And we can see that 0 is our absolute max, which might feel weird, saying that 0 is a maximum value, but if we look at the three choices we have, 0 is the largest because the other two are negative numbers, and we know negative numbers are smaller than 0. So here was an example of finding absolute extrema. It's very similar to finding the local extrema, where you calculate the critical points. But with absolute extrema, you have to check the closed endpoints of the interval. Now, the truth is that there's way more to talk about with maxes and minimums of functions. At this point, all we know how to do is find where these extrema can happen, and then we need to use a graph or comparing values to decide if we have a max or a min. But actually, there's a way to do this analytically. So we will learn how to do this in the next section. We first have to learn the mean value theorem, which is section 4.4. So for now, we're just going to practice finding the critical points and working with absolute extrema on closed intervals and using graphs to determine if we have a max or a min.